Okay, here I am once again, John Joshua Belonia, to report to you the results of experiment number 2, Python literals and operators. So first, let's open up Python. Okay, and then let's start with the experiment. So our objectives here is still to be familiar with the print function, but this time we're gonna practice coding strings using literals and experiment with the various operators. So I have read over this background and here are the results. So first, let's create a source code for expecting this output, but as the instruction has pointed out, it should be outputted on 3 lines. So as you can see here in my code, I have first type I'm learning Python, this long code, and then I've used the single quotation mark here in the beginning and the end of the code so that all the double quotation marks would be included in the output of the code. After which, the next problem would become this apostrophe. So because I've used the apostrophes here in the beginning and the end, it would not be included. But in order to include it, I used the escape character, the backslash. So I've used it before the apostrophe. And then I've put the new line function and copied the code 3 times and ended it, of course, with the apostrophe. So let's try this code that I typed beforehand. So as you can see, I've outputted this into 3 lines. So that was a successful attempt. Okay, so for number 2, it is about the observation of the exponential operations. As you can see, the double asterisk here denotes the operation of raising it to this power. So this would be 2 raised to the 3rd power and same. So everything is the same except that we observe some decimal points here. So let's just print this everything one time, big time. Okay, so as we can see, only the first output, the first answer wasn't having a decimal point. The rest were having decimal points. That's because the givens here have decimal point here, here, and then in this case both. So my observation was the operation proceeded as expected, of course mathematically. However, whenever there is a decimal point with the givens, the answer would return appearing with the decimal point even if it is unnecessary. Because 2 raised to 3 would be just 8. You don't need to say 8.0. But since the givens has, or at least one single decimal point, the output, for some reason, intentionally had a decimal point. So that goes for this rule. So let's see for the other operations. How about this multiplication operation? Let's see. As you can see, only the first print function has no decimals in it. The rest has decimals in it. So I presume that only the first one would have no decimal points in the answer. Yes, as expected. So basically, the operation was still proceeded mathematically, but the decimal point that is unnecessary was still present due to its presence in the givens. Still the same observation. Now, this trend is quite going dramatically. So let us observe if it is also true for other operations with regards to the decimal point, not mathematical. Okay, now let us observe the division operation. So let's copy this. And let's see what happens if we input it here. As you can see, only the first one doesn't have a decimal point in the given. Let's see if this same principle holds true. Let me repeat the first line, because the first line outputted here an answer with a decimal point even though it has no decimals in it in the given. So let's try executing it one other time. So as you can see, it is consistent that no matter no matter the presence of decimal point in the division operation. As of now, the division operation displays the answer automatically in decimal form. So, as the observation was written, the operation proceeded as expected mathematically. However, there is a decimal point in the answer even if it is unnecessary. Whether there is a decimal point in the given or there's not, the answer would still have a decimal point. That is for the division operation. Let's see. How about this integer division arithmetic operation, or otherwise known as floor operation? The floor operation functions as getting only the quotient and not the decimal point or the remainder in a division operation. So basically, it rounds off the quotient to the nearest or to the lowest integer that it has. So let's say 6 divided by 4, it would probably present only 1, because 6 divided by 4 is technically 1.5, but since it is a floor operation, it would be 1 only, because 1.5, the nearest integer with 1.5 to the lowest would be 1. So let's see if this still obeys the rule that was present in the exponential and the multiplication, but is defied apparently by the division operation. Let's see. Okay, so as you can see, only the first print function and the fourth print function doesn't have a decimal point in their answers, and their given also has no decimal point first, and here was the 1 2 3 4 fifth. I'm sorry, it's the fifth. So the fifth also has no decimal point in it. So as we expected, 6 divided by 4 in the floor operation would be 1. So if you inserted a decimal point, that's only the time that it would demand a decimal point in the answer. Same. So that is for the division. So how about the number 6? Imagine that we use the division operation instead of the floor operation. Could you predict the results? So let's print -6 floor operation of 4. Why have I answered -2? Because first of all, it has no decimal point, and for the floor operation there are no decimal points. So -6 divided by 4 would be -1.5. And as you may have already known, the floor operation rounds off or picks the lowest integer nearest to the number. So -6 divided by 4 should be -1.5. But since the floor operation wants to get the lowest integer that it has, so -1.5, what is the nearest lowest integer with -1.5? That wouldn't be -1, because -1 is greater than -1.5. So what is lower than -1.5? That integer would be -2. Thus, the answer -2 here. But for formality, let's still operate this. Okay, yeah, -2. And another one for this floor operation. Yeah, -2.0 because of the decimal. So how about if we formally have it at division? So it would be -1.5, of course. Yeah, so I've already explained why that did happen. This is because the floor operation wants to get the lowest integer nearest to that number, to that fraction or decimal number. So number 7, let's observe the output for each remainder arithmetic operation. So for this, the percent represents the remainder operation, which only gets the remainder out of these numbers if these numbers are divided with each other. So 14 divided by 4 would be, of course, 3 remainder 2. So knowing that it is remainder arithmetic operation, it should be 2, and no decimals in here because the given has no decimals. However, if we do have decimals, what would be the case? Of course, it would have decimal, right? So 12 divided by 4.5 should be 2 remainder 3. So since it is a remainder operation, it should be displaying 3. Let's go. Oh, 3.0 because it was decimal. Yeah, it's 3.0 as expected. So it's the same rule as always. How about we add the numbers? So if we add the numbers, of course, it would still display no decimal for the given that has no decimals in it. And yeah, same rule, same rule. Okay, exercises. So, what is the output of the following snippet? So, let me answer this quickly. So, 2 raised to 4 should be 4 times 4, 16. So, that would be 16. Then the second one would be 2 raised to 4 with the decimal point. So, 16.0 because it has a decimal point. The third one would be 2 raised to 4 with the... oh, no, sorry. This is 2 times 4, right? So it should be 8.0. And then lastly, you have 2 times 4 would be 8 without any decimal. So let's check if our answer is correct. 16, 8.0, and 8. 16, 8.0, and 8. Okay. How about the second batch? We have negative 2 divided by 4. So that would be negative 0.5. 2 divided by 4 would be positive 0.5. 2 divided by 4 with the floor, so that would be 0.5, but since it would want the lowest integer, that would be 0 because it is a floor operation. Negative 2 divided by 4 would be negative 0.5, but since it is a floor operation, the nearest lowest integer with negative 0.5 would be negative 1. So it would be negative 1 with no decimal at all, of course. Still abiding with the rules. Let's see. So we have negative 0.5, 0.5, 0, and negative 1. So it's correct. So for the third, so 2 divided by negative 4 would give it negative 2, because negative 4 times 1 would be negative 4, but 2, so remainder negative 2. 2 divided by 4, of course, remainder 2 because of 0, I guess, and 4 with whatever the reference point may be. 2 raised to 3 raised to 2. So we'll first figure out 3 raised to 2 would be 3 squared would be 9. Then this would be 2 raised to 9. So 2 raised to 9 is also equal to 2 raised to 4 times 2 raised to 4 times 2. So 2 raised to 4 is, as we've answered back then, 2 raised to 4 would be 16. 16 times 16 is 256. 256 times 2 is equal to 512. Don't get mad at me. I have played 2048 quite a bit. You know, the game that would make you forcefully memorize the powers of 2. Forcefully. Some game it is. So let's execute it. Yeah. So for conclusion, so as a general rule, if the numbers involved in any operation contain a decimal point, it is absolute that the answer would appear having a decimal point, even if it is needless, because you don't need decimal points for integers. Take note that only the division operation displays answer with a decimal point by default. Even if it is needless, it will be still displayed with the decimal point by the division operation. Arithmetic operations still operate as expected. Recommendation: it is of utmost importance that the coder be aware of the different operators in Python to avoid complexity of code. This is proven true with modulus, floor, exponential, and remainder operations. Of course, it would be a longer code if you didn't have the modulus operator, floor operator, exponential operator, and remainder operator. It would be a very long code indeed. So that's all for it. Thanks.